Okay, let's solve this LeetCode daily problem. Like, we're given an integer array, and we can perform this operation. We'll choose an index I that we haven't picked before, and then we pick a prime strictly less than the number at this index, and then we subtract this p from nums I. That is the operation we can do. And what we're asked to do is to check if we can make nums a strictly increasing array using the above operation, and if this is not possible, we'll return false. Let's look at this one. We have 4, 9, 6, and 10. So it says in the explanation, in the first operation, pick 0, and then it chooses prime 3. So I don't know why they are doing this, but let's just say we choose prime 3 and subtract it, and then we're going to have 1, and then it chooses index 1 and subtracts 7, a prime that is less than 9, and then at the end we end up having 1, 2, 6, 10. And this is a strictly increasing array. So we have 1 is less than, strictly less than 2, and 2 is less than 6, and 6 is less than 10. So we return true. Here it's already strictly increasing. It's 6 less than 8, 8, 11, and 11 is less than 12. So we return true without doing any operations. In fact, I'll show you that you can do some operations. And then we have nums. Here that it can be shown. It says that it can be shown that there is no way to perform operations to make sum sorted in strictly increasing order. So the answer is false. Yeah, we have, for example, this pair here. 8 is greater than 3, so we don't want this. It has to be strictly increasing. So for 8, we choose a prime. So we can choose, for example, 2, and subtract it. Then it's going to be 6. 6 is still greater than 3, so we don't choose 2. And let's say we choose 5, and then we subtract it. We have 3. 3 is greater than or equal to 3, so it's not strictly smaller than 3. So for this reason, we choose 7. So this leaves us 1. 1 is less than 3. But doing so creates another pair out of order. 1, 5, 1. So here we'll have 1. So 5, 1. Then 5, 1. In this case, we have to subtract something. So we have to subtract 5 to have 0, 0, 1. So otherwise, because the only value that is less than 1 is 0 in this case. Or we can have negative values, but in order to have 0, we have to subtract 5, the prime 5. But the value that we choose, p, has to be strictly less than nums I. So when I looked at this problem, well, actually I immediately see the grid idea, but I wasn't sure how to implement it. And actually, the way I was thinking about it made it harder when I first looked at this problem. So then I found a different point of view and solved it really easily. But before that, the core of the new idea, which helped me solve this, was almost the same as the previous one, but there was a slightly different approach here. I don't know what did they do in editorial, and I actually looked at the hints. Well, I don't know. I don't believe it helped. It says, think about if we have many primes to subtract from nums I, which prime is more optimal? Well, I thought about it before looking at hint 1. Actually got the same idea, but the hint 2 threw me off. So it says the most optimal prime to subtract from nums I is the one that makes nums I the smallest as possible and greater than nums I minus 1. This is similar to my idea, but there is a little different stuff. So I wasn't completely get what they mean. So I haven't looked at the editorial. Let's see what they have down there. Overview. Okay. They use the greedy algorithm and sieve of irritosness and the brute force. This, okay. I don't know what they do as their greedy approach, but let's just skim through it. Okay, then storing the primes. Well, this is just for optimization purposes, I guess. The C for 1000 is plus 2 pointers. Oh, I didn't think about anything related to 2 pointers. Well, actually, I want to see my own intuition. I want to see how could I reason that this is the correct approach. And I'll show you what I did. I don't know, in editorial they did a little slightly different stuff, I guess. But let's see how we can solve it. Now, this was how, first when I looked at it, this is how I was thinking about this problem. Okay, looking at the first input, it was 9, 6, and 10. I said, okay, if I found such an I, nums I is such that nums I is greater than or equal to nums I plus 1, then what should I surely do? Like, if you're given like 1, 2, 3 as your initial array, since it's strictly increasing, you don't care about anything over here, right? You wouldn't do any operations, or would you? So that's a question, but you actually wouldn't, because you already have your purpose, your end goal. So you wouldn't do anything if you're given 1, 2, and 3. But what in this case, there is no such pair. But here we have, for example, we have 9 and 6 here. Now what we want to do is to decrease nums I. For this, what is our operation? We choose a prime, right? So this prime has to be less than nums I. Okay, it has to be less than nums I. And this should make nums I less than nums I plus 1. So how do we do this? But while I thought that, okay, if I'm making nums I smaller, I just make it just smaller than nums I plus 1, not too much. So that if I decrease this one too much, then I have a high potential to make the previous value before nums I, basically nums I minus 1, greater than or equal to nums I. So in order to avoid this, hopefully avoid this, I said, okay, let's just decrease nums I such that it is less than nums I plus 1, but it is greater than nums I minus 1. So we just decrease nums I by the prime such that it becomes less than nums I plus 1, but it's still as large as possible, so that we avoid this issue here. But that was my idea. But still, this does not guarantee, because that's not a proof, that once we do that, we won't have any such pairs. We won't create this situation here. But we do. We actually create such a situation. For example, let's see 9 and 6, right? So for 9 and 6, there's a difference of, okay, what's going on here? Okay, I guess it's removing. Okay, what's going on? Sorry for this problem. I have a little glitch with this website. Okay, now we have 9 and 6. So 9 is greater than 6. So we have to subtract a prime. So what's the difference? We have 9 minus 6, which is 3. So we have to subtract a prime, pi, such as that is, let's just say p, that is greater than 3. So let's find a prime less than 9 but greater than 3. The first prime that is greater than 3, because we don't want to decrease this value 9 too much. So we'll subtract a prime as small as possible that is greater than 3. But so there we have 5, there we have 7. So the first value that is greater than 5 and 3 is 5. So we subtract 5 from 9. If we subtract 7, we make it too small. For example, 4, 2, and 6. This definitely makes 4 greater than 2. So that's another pair that's out of order. But so for this reason, we subtract 5. Well, actually, subtracting 5 still creates an unordered pair. So we're going to have 4 and subtract 5, 4, 6, and 10. Now, you see what happened? We fixed a pair right here, but we created another pair that is out of order because 4 is greater than or equal to 4. It's not strictly less than. So now we have to decrease 4. So the same happens. We decrease 4. What is just found the difference? It's 0. We have to find a prime that is greater than 0 and less than 4. It's 2. And then we subtract 2 from this 4. Then we have 2, 4, 6, and 10. This is what they had, I guess, in the first one. Okay, not really. They have 1, 2, 6, and 10. That's another way. And I have 2, 4, 6, and 10. So this was my idea, and I was sure that this is a valid idea. But there was a problem when you have, let's just say, abstractly an array. Let's say we have an array, and for here we have I and I plus 1. Let's say this value here, x and y, x is greater than or equal to y, right? So for this reason, we subtract a prime from x. So then we'll have a value a, let's say. And now we might create another pair that is out of order. But because imagine that this part here is fine. That means it's already increasing. So this is already increasing, right? This array, we have, like, let's say xi, x1, x2, x3, and x1 is less than x2 is less than x3. Okay, I hope you get the idea. This is already increasing. So what I want to say is that we create a pair here that is, we have x, we have a, and there might be something here. Let's say xi minus 1. Xi minus 1 is not greater than or equal to a. Now we need to decrease xi minus 1. So that was my problem originally. And then I said, okay, let me start from here and go to the first value and do what I want to do. If I haven't already decreased this value, if I've already decreased this one, then I won't be able to decrease it again. So in this case, what do I do? Like, is it false or is it not? And then I asked, okay, if I've already decreased this one, why not decrease it as much as possible so that it becomes, very, very small, that it will not affect the future operations. For example, if this xi minus 1 was quite small, it could have been possible that when I decreased x by p, then I got a, x minus I will be less than a. So x should have been decreased. I guess, okay, now I got it. They meant this by in the hint 2. Okay, I've done a different stuff though. But for this reason, this led me to do another thing. Since when I decrease x by p, this creates a problem with the previous values, because I've already processed them, this part of the array here, and now when I decrease x by p, this creates a problem because I have to go back and fix the other values, like going to the past, like fixing your mistakes, like correcting your mistake. It's like this. So for this reason, I didn't want to like interfere with the previous operations. So how did I avoid this? I start from the right, because once I have a value, now let me explain this. Okay, for this value, let's just keep it as big as possible, because there's no reason not to decrease it. This only could make the previous value bigger than this one. So let's just keep it as it is. And now we start here. with this value. Let's call it x, and let me actually take red. Let's call it x, and let's call this y. And if x is greater than or equal to y, now my idea works here. Let's decrease x so that it is less than y, but we keep it as big as possible. So we'll subtract such prime such that it will be as big as possible. It will stay as big as possible while being less than y. So that was my original greedy idea. And then after I do this, I'll go to the left, and there could be like other values. Let's say this was xi, this is xi minus 1. If xi minus 1 now is greater than x, we'll fix xi minus 1. But fixing xi minus 1 will never because we're making this smaller, and it will not have any effect in our previous operations, as opposed to our previous idea. Here, when we change this x, we have to go back to our, to the previous values and do some fixes. But now here we don't have to do that. We don't go back and do fixes. We just, if this is out of order, if this is like x greater than or equal to y, in this case, if xi minus 1 is greater than or equal to xi, then we're just going to decrease xi minus 1 by a prime, such that the same idea applies to this one, such that it becomes less than xi, but it stays as big as possible, such that the previous values are smaller than this. So this is the greedy idea. So then we decrease it, and then we do the same thing for this one, do the same thing for this one, and do the same thing for this one. If there will be such a value that we won't be able to do that. Let's say at this point, there's two values here. For these two values, let's call it, like say a and b, and a will be greater than b. So we need to subtract a p. So it's possible that there is no way that we can do that. Well, it could be that we don't have a p such that it is less than a, and such that it's less than a. And when you subtract p from a, we'll get something less than b. In this case, we don't have, if we don't have a prime to subtract from a to make it less than b, then we're just going to say, okay, stop here. So we failed to do this. So that is the greedy idea that I applied. Now let's see the code. So submission, I did it a while ago. So first of all, I collect primes. For prime, they used actually CBOB Erasmus. That's much more efficient than the trivial division here. I used, I go to up to the square root of n, and then check if a given value is prime. So here I initialize the primes array. I go from 2 to 1000. 1000 is the max value that could be in the array. And I collect the primes in the primes vector. And then I go down here, and we have a flag value. It says true. And if we find such a pair, just as I said here, if we find this AB pair, then we'll make it false and break from the for loop here. And we start from the second to last value and go to the first value. And if numzi is greater than or equal to the numzi plus 1, the next value, I find the difference here. Let me say, okay, for example, when we have 9 and 6, I found that there's a difference of 3. So I have to subtract something that is greater than 3, so that I will make it less than 6. I have to subtract something that is either 4 or greater than 4, right? So basically, I will subtract a prime that is greater than 3. So that, for this reason, we use binary search. In our primes array, we'll search for a value that is greater than 3. For this reason, we can use the standard library function upper bound. Upper bound finds, it takes upper bound, it takes the range that you're searching. So we give the begin and end of this prime, this begin and end, and then we give the value. It finds and it returns an iterator pointing to an element. Let's say this is this element, such that its value is greater than the given value. So for it, we'll use upper bound for this purpose. So then we use upper bound prime and then find a value that is greater than x. If we couldn't find it, if such that it does not exist in our primes list, or we find but it is greater than nums I, because the problem statement says that we have to subtract a prime p strictly less than nums I. So then we're going to put false and then break if this is the case, because we couldn't find it. Otherwise, we decrease the nums I and move to the leftmost element, and then at the end we return okay. This was actually a nice problem, and for those who are mathematically inclined, actually you can see it's greedy and binary search and number theory. That's a nice problem, and I actually learned something different. You know, once you know that your greedy idea might be correct, but trying it one way does not yield anything, and try it another way. You see, when we do the decrease the first time, we're actually creating the potentially creating a pair that is out of order, and then we have to go to the left, which we've already come from. So we come from left to right. So we come from left to right. So going back to left, this is a little bit, unintuitive. Like how I'm gonna like implement this in the code. Well, you can actually, maybe I could have done that, but this would be O n squared, ignoring the prime case. Ignoring the primes, this would be O n squared. But in this case, we actually start from right and go to the left. When we do a decrease, it does not affect the values. It only affects the values on the left. It only creates a out of order value on the left side, which we're moving to. So we're moving to left, and we'll fix it anyway. So it does not affect the right side, which we come from. So that was the idea. I hope you understand. I hope you liked it, and I believe this is quite convincing. And if you have any other idea, write it in the comments, and I'll be glad to see. And I'll read the tutorial now. We'll see what they have there. But that was my idea.